Let's look at part 2 of chapter 28. We're going to be looking at refraction and mirages. Anyway, so let's look at refraction. So this block sort of tells the whole story. So let's just examine this block. And so the idea with refraction is that the angle changes as light goes from one material to another. So we discussed this a little bit earlier when we talked about the index of refraction. And so let's look at these angles here. So here we have a beam coming from the air and then going into a block of glass. And it slows down when it goes into the glass. So first of all, we're going to have to say, okay, well, this air is faster. And up here, the glass is slower. Okay, so what else is true? So let's look at the angle. So we're going to draw a normal surface. Okay, so we're going to draw a line that's normal to the surface here. And we're going to look at the angles. So this angle looks like it's about 45 degrees. And that would be the incident angle. And the refracted angle, you can see, is smaller. That looks more like it is maybe 30 degrees. So now we've learned something else. Where it's faster, it has a larger angle. And where it's slower, it has a smaller angle. Okay, so faster, of course, remember, would be a smaller index of refraction. Where it's slower, that would be a higher index of refraction. So like we talked about how light slowed down in a diamond. Okay, now notice where this comes out on the other side. Because these two sides are parallel, it's coming in at 30 and leaving at 45. So now we've learned that it doesn't matter if the light is going from the faster to the slower or the slower to the faster. It still works out that the angles are linked to the speed of light in the material. Okay, so what are the rules then? Okay, so refraction itself is the bending of light when it passes from one material or medium to another, and that's caused by the change in the speed of light. And there's some illustrations like this that try to get you to understand it. So like here we have a cart, a wagon or something that is gliding along, and of course it would have 4 wheels, but we don't need all the wheels. And the thing is, the front wheel here starts to drag on the grass. And so when it drags on the grass, that slows it down, and the other wheel is going faster, so it gets ahead. And that changes the angle. So now when the cart hits the grass totally with both wheels, it actually is going at a different angle now. So you end up going at a different angle. And if you'll notice out here, it was faster. And when it was faster, it had a larger angle. And I'm going to use this symbol for angle because I'm tired of writing it. Okay, and down here, where it was slower on the grass, it again had a smaller angle. All right, so it works, right? So that's the idea, is that the wave front kind of gets bent over. And we looked at this when we looked at sound. So we looked at the idea of waves coming into shore and how they were slowing down and how that changed the angle. So the same thing is happening here. We've got some wave fronts coming. So wave fronts, so imagine beams of light coming in, and all the Waves are, locked in step here, and all the wave fronts are coming in, but this side of the wave starts to hit first. It starts to slow down when it's in the water. The other one is going faster, so that makes it curve around. And again, now you've got a smaller angle where it's slower, a bigger angle where it's faster. Okay, so it looks like we have a very solid group of rules there. The angle of incidence does not equal the angle of refraction. And you get a smaller angle where it's slower, a bigger angle where it's faster. Maybe I should actually write that down someday. But I expect students are going to listen to me, so I expect them to write it down. Okay, so light rays bend as they pass from air into water, water into air, water to glass. So here we've got a spoon that you can see in the top of the glass looks broken from the bottom of the glass. And that's because the light has to go through the layer of water also. And so the angle keeps changing. So when the light reaches our eyes, they don't look like they're coming from the same place. Now, there's a guy who likes to take water drop lens images, which are upside down. So this one was flipped, but the real goldfish is back here. Here's 4 water droplets and a big eyeball back there. He says he does on Photoshop. Here's an astronaut doing sort of the same thing. This is in space, this International Space Station. And Andre here made a bubble of water and then injected it with a bubble of air. And so he and the bubbles are in free fall, and you can see his face got turned upside down or reversed here, and then reversed again because of the bubble of air. Okay, so another example your book likes to use is the idea of a lifeguard. There's a person in distress down here. If the lifeguard just went straight towards the person, then they wouldn't get there the fastest, because the lifeguard knows that he can go faster on the sand running than he can in the water swimming. So the lifeguard instead tries to spend more time on the sand, and so reaches this point before he starts to swim, because that will actually be the shortest time. So that's still that idea of principle of least time. The light beam will take the path that has the least amount of time to your eyeball. Okay, so here's a fish. And one of the things is that because when you look at fish, they are underwater, unless you're underwater too. But when you're out of the water, when you're in the air, the image of the fish that you see is not where the fish really is. What happens is the fish has light beams radiating in all directions. Some of those are going to come at the right angle so that then when they refract at the surface, they come to your eye. But the thing is that your eye doesn't know that it refracted, so it follows those beams backwards and thinks that the fish is higher up than it actually is. And oh, I didn't set up that demo. I'll have to do it in class. So yes, so refraction has the raising up of the image. And so this is why if you step into a stream, which has nice clear water, you may think it's shallower than it is. Okay, so you think, oh, it's just a few inches deep, and then your foot plunges down a foot into the water. So yes, you can be deceived by the water raises things up and makes them magnified, makes them look larger because it raises them up. Now, we already talked about refraction with sunlight. As it at sunset, it actually will curve around the planet because the different densities of atmosphere cause the light to refract. And so your eyeball follows it backwards and sees the sun higher up in the sky than it actually is. So when you're looking at a sunset, sunsets can last longer than they actually should, because what's happening is that you are keeping parts of the sun that should be not visible above the horizon. So your brain has followed that light beam back. And this is why the sun makes this lemon drop shape, is because you're seeing the top and the bottom of the sun kind of squished up into the same place because of the refraction through the atmosphere. Okay, which leads us to mirages. Now, mirages happen also because when it's very warm, you get air that is less dense because of the warmth, and other layers of air that are more dense. So what happens is that this will cause light to bend. And so let's say you're out there and you're looking for a place to get a drink of water. The light from this palm tree will actually bend and reach your eye. But again, you don't know that it has bent, so you follow it backwards and you think that the tree is here. That's where it intersects with the ground. And so the thing is, you think it's really half as close as it actually is. So you start to walk towards it. And the thing is, as you walk towards it, the mirage just keeps moving ahead of you. And so the actual oasis is twice as far, and you never reach it because you're always seeing it as half the distance to its actual location. So anyway, so this is a problem out in the desert, especially when people see things like this, because it looks like there's puddles of water or a lake out in the desert. Well, that's not. That is actually an image of the sky, which reflected up and into the eyes of the person looking out. And so this is extremely dangerous for people who are like the pioneer days when people would cross the desert, and some people would leave the trail because they thought they saw water out in the desert, but it wasn't water. And so you'll see this also on hot roads where it looks like there's a puddle of water in the road. And here you can see like this looks like a motorcyclist is reflected in the water, like there's some sort of puddle here. If you get to drive to Wisconsin, it's really fun when you're going up and down the hills because this happens over and over again. You'll see a mirage and then it'll disappear as the angle changes. You'll see them around here too, but the hillsides help you to see them over and over again in Wisconsin. Okay, so that's the idea with that part, and we're going to go on and look at dispersion and rainbows and total internal reflection and lenses for part 3.